One of the places where we saw the chain rule a lot in Calc 1 was in implicit differentiation. We can kind of look at this case again. Usually we had some function of x and y, right, that was equal to a constant. So it wasn't exactly spelled out how y depended on x. If we think about this situation, we can actually use the chain rule to find how y depends on x, because we have here this function f, and the output of this function, apparently f depends on both x and y, right? But then they're asking us to find dy dx, so we can assume that y itself depends on x. Then according to the chain rule, df dx, so the derivative of f with respect to x, which we can see f of xy is actually a constant 0. So if you change x, then f can't change. That's equal to 0. But also by the chain rule, if you make a change in x, that will change f. So we could look at changing x, how changing x changes f, right? But then we can say, well, changing x could also change y, and changing y could change f. And this gives us an equation that we can solve for dy dx. You notice if we move the df dx over, we find that dy dx is equal to negative df dx divided by df dy. Or that would be negative f sub x over f sub y. Okay, so let's look at an application here. Can you see that here we have a function of x and y, and it's set equal to 0. Then following this formula, dy dx is going to be equal to negative f sub x. The partial of this function with respect to x is e to the y, and the derivative of, let's assume that's sine of x times y. The derivative of that with respect to x is y cosine xy. You take the derivative of the outside divided with inside times the derivative of xy with respect to x is just y. Okay, and then the rest of these have derivative 0 with respect to y. Then we divide by the derivative of f with respect to y. And the partial of f with respect to y is x e to the y. And the partial of this with respect to y is x, let's see, the derivative of sine is cosine xy times the derivative of what's inside. That gives us the x out here. And then finally the derivative of y with respect to y is 1. So we have dy dx is negative f sub x over f sub y. So we found it just by using this formula that comes from our multidimensional chain rule. Often in the chain rule, it's not so much that you're looking for the derivative of the composition as you're trying to find one of these other total derivatives. So in terms of matrices, then if I knew this derivative and I knew that derivative, then I could solve for this derivative by multiplying both sides by the inverse. So dh times the inverse of this matrix, if it exists, is equal to df. So a lot of times in the chain rule, you're not necessarily looking for the derivative of the composition. This may be a value that you already know what its derivative is. You're just interested in one of the derivatives in the product, so you're going to use the chain rule and then solve for one of those particular derivatives. Now here's a simple example. We have t, right? And given t, we find this value s, and given s, then we can find this vector valued function r. So we have a chain here. Both of these matrices, let's see, this matrix, since there's one input and one output, scalar input, scalar output, then that's going to be a 1-by-1 matrix. And then here we have a scalar input but a vector output, so that's going to be like a 2-by-1 or 3-by-1 depending on how many outputs R has. But anyway, we can find dr dt. This is the derivative of the computation of the composition, right? R depends on just one thing, t, after the end of the composition. But that should be equal to the derivative of r with respect to s. So the derivative of r with respect to s times the derivative of s with respect to t. So if we knew what dr dt was and we knew what ds dt was, then we could easily solve for dr ds by dividing both sides by this scalar ds dt. So we end up with dr ds is equal to dr dt divided by ds dt. We'll actually see that we have a lot of application to do this with the chain rule in several cases in the next chapter. So we're going to be analyzing motion, and this is going to be something important. But keep in mind that that's how the chain rule often works. You're not necessarily trying to find the derivative of the composition. Maybe the composition is something very simple, and so you know its derivative, but you're actually looking for the total derivative of one of the other functions in the composition.